Hello everyone, my name is Norouzpour. I received my Ph.D. from University of Victoria in BC, Canada. Unfortunately, I wasn't able to attend M&M conference this year. I would like to thank Nicole Guy, the meeting manager, Michael Gribolyuk, and all the symposium organizers for giving me the opportunity of presenting my work through this video. This means a lot to me. I have left my email here in this slide, mananrp@uvic.ca. I will appreciate your questions, comments, and feedback. My presentation is about reconstructing the phase and the atomic displacement profile through the specimen thickness using self-interference of a split hole. First, I would like to start with the motivation of this work, which is followed by introduction. Then I will present the methodology, which is the analytical approach of the work. The experimental procedure is already presented in details in my published papers. I will show you the references and shortly review the experimental setup. Finally, I will wrap it up with some results, conclusion, and future work. A property of the majority of semiconductors is the presence of lattice strain changing with the nanometer scale. For example, a strain originates from the lattice mismatch between layers of different composition deposited during epitaxial growth. A strain is usually considered as a limiting factor, although it can increase the mobility of the charge carriers by the band gap reduction. So, measuring atomic displacement inside crystals is an important field of interest in semiconductor industry. Among all the available techniques measuring a strain inside crystals, transmission electron microscope is the only tool which enables us measuring the atomic displacement with nanometer scale. In transmission electron microscopy, methods to measure nanoscale atomic displacement include image-based, diffraction-based, and electron holography-based techniques. I'm not going through the details of these techniques, only to let you know, among all TEM techniques offering nanoscale resolution measurements, convergent beam electron diffraction patterns show the highest sensitivity to the atomic displacement. Higher order Lowy zone HOLZ lines split by small variations of lattice constant. This allows the atomic displacement measurement through the crystal. However, this is a cumbersome measurement. Except electron holography, all the other techniques use the electron beam intensity to measure a strain, while the atomic displacement information is actually inside the phase of the diffracted beam. Dark field electron holography is a technique which reconstructs the phase of the diffracted beam to study a strain inside semiconductors, although it only measures it in 2 dimensions. Several attempts have been done to simulate the 3rd missing dimension using the 2-dimension experimental information. The 3rd dimension is through the specimen thickness parallel with the beam direction. In this work, I combined convergent beam electron diffraction technique with the electron holography to directly and experimentally reconstruct the phase across the split HOLZ line. This carries the z-dependent atomic displacement profile, the missing dimension profile. In this slide, you can see the effect of a hypothetical bend in crystal on the HOLZ line. Assuming a non-strained crystalline plane, the electron beam will be Bragg diffracted onto a HOLZ line at B in diffraction space. While in the presence of a bending as shown, the HOLZ line splits into 2 main intensity peaks at A and C and some internal intensity peaks. Here in real space, R max is the maximum atomic displacement, which in some works it is called the atomic displacement amplitude. Many researchers have used either kinematical or dynamical theory of diffraction to simulate the intensity profiles across the split-HOLZ line. They have simulated these intensity profiles for various displacement profiles, such as a V-shape or a triangle, parabola, or a bell-shaped profile. The atomic displacement profile are shown in the first row of figures in this slide. In all the proposed intensity profiles, the common property is the split width, which increases as R increase. However, the internal intensity profiles vary for different atomic displacement shapes. This is actually the principle of the SIS-HOLZ technique. By SIS-HOLZ, we recover the phase information across the split-HOLZ line to determine the z-dependent atomic displacement shape. I presented the experimental details of this work in some of my publications, which actually are integrated in this slide. But as a short summary, in SIS-HOLZ technique, consider specimens such as silicon-silicon germanium superlattices. In the silicon region close to its interface with silicon germanium, which is highly strained, we apply the seabed technique and we get the split-HOLZ line. This is shown on the left figure. Then we call the biprism, which shares the same plane as the selected area aperture. We focus its image on the diffraction plane, align it in the middle of the split parallel with the HOLZ line. Then, by applying some voltage on the biprism, two sides of the split HOLZ line are deflected towards each other and they self-interfere. This is shown on the right side of the figure. So here we get an interferogram. The interferogram is then Fourier transformed, as you see. We get two sidebands plus one center band. One sideband is filtered with a proper window, and applying the inverse Fourier transform results in the phase image, and subsequently we can reconstruct the phase profile. Now let me elaborate on the main contribution of this work. We require an analytical approach to justify the results and quantify the atomic displacement. Here, I used kinematical theory of diffraction, which is acceptable if the specimen is quite thin. For example, for any particular HOLZ line, it must be below the extinction distance over pi. To develop the analytical approach of this method, I borrowed the Howie-whelan equation, which gives the diffracted amplitude at the exit surface of the specimen. As you can see in this slide, R is in the phase of the equation. Actually, R is in the phase factor of the Howie-whelan equation. T is the thickness and S is the excitation error, which is the deviation from the Bragg angle. Assuming a symmetric band, to develop an analytical approach, I applied the experimental steps on the Howie-whelan equation. I inserted different atomic displacement profiles of V-shape, parabola, and bell shape into the Howie-whelan equation. Then I split it into two halves. One half is coming from the top part of the specimen, and another half is from the bottom side of the specimen. This is where I call the biprism and align it right in the center of the split. Now it is time to apply the voltage, so I'm adding extra phase shifts relevant to the biprism and its deflection angle to the split waves. Finally, I add the split waves to get a resultant wave. The arctangent of the imaginary part over the real part gives me the phase as indicated. The introduced wave solution is used to simulate the phase profiles for 3 typical atomic displacements. You can see the atomic displacement profiles on the left and their corresponding phase profiles on the right. Now, let me compare these simulations with the experimental results. Here in this slide, we see bright field disk and their corresponding dark field disks for 008 Holz line. The first image on the left is 400 nanometer away from the interface of silicon and silicon germanium. We have individual Holz line here. By approaching towards the interface, which is shown in the middle and right figures, we see the individual Holz line splits and the split width increases. At an optimum distance from the interface, which the intensity of the peaks is high enough to self-interfere, we apply the SIS-HOLZ technique. You can see the position of the biprism with respect to the split Holz line. Now, here in this slide, we have the experimental interferogram. Some regions show the intersections of other Holz lines. They give complicated phase profiles. The region of interest for this study is actually the clean areas with no intersection of other Holz lines. We reconstruct the phase image using the sequence of Fourier transform, filtering, and inverse Fourier transform. Comparing the experimental results and the simulated solution gives the best match for the bell-shaped displacement profile. The details of this approach is presented in the Journal of Micron as indicated. In this paper, you will see the difference of other profiles for various Holz lines and different thicknesses as well as the atomic displacement amplitudes. The best match for the examined 008 split Holz line at 80 nanometer away from the interface was the bell-shaped profile with the maximum atomic displacement of 0.0325 nanometer. In conclusion, I believe that the SIS-HOLZ technique enables measuring the atomic displacement profile through the specimen thickness by reconstructing the phase profile across the split Holz line. The kinematical approach for quantifying the data looks promising if the thickness satisfies the kinematical condition for the electron diffraction. The only parameter which affects the shape of the phase profile was the atomic displacement shape. This is shown in details in the paper I just introduced in previous slide. In order to modify this method, I'm interested to apply the same approach considering the dynamical diffraction effect. Also, in the presented analytical approach, the atomic displacement is symmetric with respect to the center of the specimen. Considering asymmetric atomic displacement profile could be quite beneficial in further development of this work. Once more, I would like to send my gratitude to M&M 2017 organizers for giving me this great opportunity. I would really appreciate your comments, questions, and feedback on this work. You could contact me through my email indicated in this slide, and thanks for your attention.